In the previous video, I mentioned that we're going to calculate the margin of error when we're dealing with a confidence interval for a population mean by using a critical value t sub alpha over 2 times s over the square root of n. This is going to be our formula for calculating the margin of error. But in order to do this, we're going to need to come up with this specific critical value, and this is a critical value from a student's t-distribution. We'll also remember from the previous video that the specific shape of a student's t-distribution is going to vary depending on the degrees of freedom. So this critical value is not going to be the same if I have, say, a t-distribution here. Maybe this is one with, say, 5 degrees of freedom versus one if I have, say, 10 degrees of freedom, may look something more like this. So the specific shape of that t-distribution is going to affect what this critical value is. So what we're going to be looking at next is how do we go about figuring out what those critical values are for the student t-distribution. So example, find the critical t-value or values described. A, the area in the right tail is 0.02 with 17 degrees of freedom. B, the area in the left tail is 0.975 with sample size n equals 20. And C, we're looking for critical values that corresponds to 95% confidence with 10 degrees of freedom. So what exactly does this mean? Well, if we take a look at part A, so the area in the right tail is 0.02 and we have 17 degrees of freedom. Well, picture-wise, I have this student's t-distribution, and again, we know that the degrees of freedom, which I'm going to abbreviate df, is 17. So the specific shape of this t-distribution is the one that has 17 degrees of freedom. And we know that the area in the right tail is 0.02. So this area right here is 0.02, and we want to find this critical value right here, which will be our t sub alpha over 2 that we would then use for our confidence interval. Now, in this case, we're not actually finding the confidence interval, but we're learning how to find this critical value so that we can calculate the confidence interval. In part B, we'll come back and find that value in just a minute. In part B, the area in the left tail is 0.975, and we have a sample size of n equals 20. Well, first of all, if the sample size is n equals 20, then that means that the degrees of freedom will be 20 minus 1, which means we'll have 19 degrees of freedom. So we do have to pay attention. Do we know the degrees of freedom or do we know the sample size? If we know the sample size, then our degrees of freedom is going to be 1 less than that. So this will be a slightly different t-distribution. So generically they have the same look. But if I were to compare this to this one would have a little less area in the tails and a little more area in the middle than this one. This one compared to this one would have a little more area in the tails and a little less area in the middle. Anyway, so in this case, the area in the left tail is 0.975. So that means this area over here is 0.975. And I want to figure out what is this t sub alpha over 2 value. Incidentally, just like with the standard normal distribution, zeros here in the center, zeros here in the center. So if I know that the area in the right tail is 0.02, then I know that value has to be positive, because the only way we're going to have an area of 0.02 in the right tail is if that value is to the right of 0. In the same way, I know that this value is going to have to be positive, because the only way we're going to have 0.975 in the left tail is if we have a value over here to the right of 0, because the 0 is going to be like the split of 50-50 on either side. Take a look here at C, and then we'll come back and actually find the values. For C, we're looking for the critical values that corresponds to 95% confidence with 10 degrees of freedom. So again, I'm going to have yet another t-distribution. This t-distribution has 10 degrees of freedom. So that means the tails on this curve compared to the other two are a little thicker, and there's a little less area in the middle. So anyway, if we're dealing with 95% confidence, then that means the area in the middle here, that area is going to be 0.95. So I'm going to have a negative t-value here. I'm going to have a positive t-value here. Those two values will be the same value, just one negative and one positive, so their absolute values will be the same. And so I want to figure out what those two values are. Well, how am I going to go about doing that? How am I going to go about finding these critical values? Well, we have three different ways that we can do this. We can use the student's t-distribution table that's provided for us in the appendix of our textbook. We can use a TI-84 calculator, and we can use StatCrunch. So I'm going to show you each of those. So first of all, let's take a look at the student t-distribution table that's provided in the appendix of our book. So that is this. So again, this is page A-14 of the appendix of your book, table 7. So first of all, take a look at the graph. The way this table's set up is different from the way the standard normal table was set up, and so we need to examine this carefully. So first of all, the values along the top row of this table are areas in the right tail of t-distributions. So we have a fairly limited table. So this is representing an area of 0.25 in the right tail, 0.20 in the right tail, 0.15 in the right tail, and so on. So if you look up here at the graph, this area right here is that area in the right tail. And so we're going to be looking up the t-value that has that area in the right tail. Now the specific value that we're going to look up is going to depend on the degrees of freedom. This far left column gives us the degrees of freedom. So for example, if the area in the right tail is say 0.10, and if we have 6 degrees of freedom, then I'm going to go to this column and I'm going to go down to the 6th row, and so that value that I see, 1.440, that would be this t-value here that has this area of 0.10 to its right. So again, if I have 6 degrees of freedom and if the area in the right tail is 0.10, then that critical value would be 1.440. But if I had 7 degrees of freedom, then that critical value would be 1.415. If I have 8 degrees of freedom, then that value would be 1.397, and so on. So the specific value that I get, again, depends on the degrees of freedom. That's a big deal. If we use the wrong degrees of freedom, then that means we're going to end up with the incorrect calculation for our margin of error. Okay, so take a look back here at Part A. In Part A, we knew that the area in the right tail is 0.02, and we knew we had 17 degrees of freedom. So if I'm going to use this table, I'm going to come to the column where the area in the right tail is 0.02. So that is this column here. And again, we have 17 degrees of freedom. So I'm going to come down this column to 17 degrees of freedom. And so I get this value right here, 2.224. So this critical value right here is 2.224 if I have 17 degrees of freedom. So there is my answer to Part A. That critical value is 2.224. Now looking at Part B, if I'm going to use our table, I have to have the area in the right tail. So in question B, I was given the area in the left tail is 0.975. So that means this area here in the right tail is going to be 1 minus 0.975, which is going to be 0.025. So this area in the right tail is 0.025. Now also recall we have 19 degrees of freedom. So if I use our table from the appendix of the book, I'm going to use the column where the area in the right tail is 0.025, and I'm going to go down to where we have 19 degrees of freedom. So that is this row here. So 19 degrees of freedom over to 0.025 in the right tail, and so that value is 2.093. So this critical value right here is 2.093. So there's our critical value. Looking at part C in the same way, I've got to have the area in the right tail. So if it's 0.95 in the middle, then the other 0.05 is shared between the two tails. Half of that 0.05 is going to be in either tail. Half of 0.05 is 0.025. So this area in this tail right here is 0.025, as is this area here. This is 0.025. So once again, if I bring in my table, I'm going to use the 0.025 column. In this case, we had 10 degrees of freedom. So using the 0.025 column coming down to 10 degrees of freedom here for this row, then the right value is 2.228. So this value over here is 2.228, which means this value over here by symmetry is negative 2.228. So we were able to look up these critical values using the student's t-distribution table from the appendix of the book. So we can also find these critical values using our calculator. Maybe. It depends on the model and age of your TI calculator. So the way you will know is this. If you go to the distributions button, so second distributions, on my calculator, number 4 says inverse t. If you have this capability on your calculator, that should be where it is. So if you have an older calculator, you may not have that option. You may not have the inverse t command on your calculator, but if you have a newer calculator, you will have that command. Now here's how that inverse t command works. We're going to choose that inverse t command, and what we have to do is we have to put in the area in the left tail. Now this is different from how it was in the table. In the table it was the area in the right tail, so we put in the area in the left tail, comma, then we put in the degrees of freedom, and the calculator will give us the critical value that has that area in the left tail with that number of degrees of freedom. So for example, if we look at A here, we knew the area in the right tail was 0.02 and we have 17 degrees of freedom. So that means the area in the left tail is going to be 0.98. So that's the area to the left of my critical value. So my command for A is going to be inverse t. So it's going to be inverse t 0.98 comma 17, and that will give me that critical value. So again, if I bring my calculator back in, I'm going to go to the distribution button, so second distribution, and I'm going to choose number 4, inverse t. Now on my calculator, I get this window that opens up. Again, depending on the model and age of your calculator, you may have to type it in directly like I've shown you here. So my area in the left tail is 0.98, my degrees of freedom 17. Now on this calculator I choose to paste, which then gives me this command. And so I get the 2.224, which is the same result we got using the table. Similarly, in question B, we were given the area in the left tail. So the area in the left tail is 0.975. The sample size was 20, which means we have 19 degrees of freedom. So again, on my calculator, I can go to distribution, choose inverse t. Again, my area in the left tail is 0.975, and I have 19 degrees of freedom. So again, this is how the command would appear, inverse t, 0.975, comma 19. And so I get 2.093, which is the same result we obtained here using the table. Likewise for C, in this case we have two different critical values. I can find either one of them. The simplest one would be to find this one here. So my area in the left tail is 0.025, and we had 10 degrees of freedom. So again, inverse t, 0.025, and we have 10 degrees of freedom. And so I get negative 2.228, which is the same that we got from the table. And by symmetry, that means this one has to be positive 2.228. So again, if your calculator has that inverse t command, then you can use it. Now, we can also use StatCrunch to find critical values for student t distribution. And so we do that this way. Go to the stat option, and we're going to use calculators, and we're going to go to the t calculator. Now this t calculator works a lot like the normal calculator works that we've used before. The difference is we have to fill in the degrees of freedom. So if I fill in, for example, for part A, we had 17 degrees of freedom. And in part A, we knew the area in the right tail was 0.02. Since I'm dealing with the right tail, I'm going to change this inequality to greater than so that I'm looking at the right tail. And then if I fill in the area 0.02 in this outer box and say compute, it will give me the critical value on this inside box here. So I get 2.224 if I round to 3 places, which agrees with what we got on the table and on the calculator. For part B, I can change my degrees of freedom to 19. And in this case, we knew the area in the left tail was 0.975, so I can change this to be less than, and then change this value in the outer box to 0.975. And when I say compute, then I get 2.093, which again agrees with what we got from the table and what we got from the calculator. In the same way for part C, we had 10 degrees of freedom, so I can enter the degrees of freedom, and we have options on how we do this one. One, we could figure out that the area in the left tail is 0.025, and so we could just enter 0.025 out here, since I have it as a left tail, and that would give me that negative critical value, which is negative 2.228, which means the positive critical value would be positive 2.228. So we could do that the same way that we use the calculator. Or, just like with the normal calculator, we have this between option. So I could choose between, and we know that the area for part C that's in between the two critical values is supposed to be 0.95. So if I enter that in this outer box and say compute, it gives me the negative 2.228 and the positive 2.228. So this is how we can use StatCrunch to find the critical values.